Introduction to Quantum Information Processing. Welcome to Lecture 11. In this lecture, I am going to show you quantum algorithms for two problems. One is called the order finding problem, and the other is the factoring problem. I will show you how these algorithms can be based on the framework of the phase estimation problem that we saw in the previous lecture. Before explaining these algorithms, I would like to review some basics about divisors, common divisors, and the greatest common divisor of two integers. Of course, we know that factoring a number is about finding its divisors, where the divisors are the numbers that divide x. If we have two numbers, x and y, then the common divisors of x and y are the numbers that divide both of them. For example, for the numbers 28 and 42, the common divisors are 1, 2, 7, and 14. 4 is not a common divisor because although 4 divides 28, it does not divide 42. For two numbers x and y, their greatest common divisor is the largest number that divides both x and y. The greatest common divisor is called the GCD. The GCD of 28 and 42 is 14. What's the GCD of 16 and 21? It's 1. There is no larger integer than 1 that divides both of them. We say that x and y are relatively prime if their GCD is 1. That is, they have no common divisors except the trivial divisor, 1. 16 and 21 are not prime, but they are relatively prime. Superficially, the problem of finding common divisors resembles the problem of finding divisors, which is the factoring problem. If x and y are n-bit numbers, then a brute force search would have to check exponentially many possibilities. But in fact, finding greatest common divisors is considerably easier than factoring. It has been known for a long time that there is an efficient algorithm for computing GCDs. When I say long time, I mean approximately 2,300 years. That's how long ago Euclid published his algorithm, now known as the Euclidean algorithm. Of course, there were no computers back then, but Euclid's algorithm could be carried out by a hand calculation, and it requires order n arithmetic operations for n-digit numbers. This translates into a gate cost of order n squared log n. Here's a picture of Euclid. His algorithm, along with other amazing material about numbers and geometry, is explained in a 13-volume series entitled Elements. Here's a fragment of the original manuscript. There was no archive for him to post his results on. Let's remember Euclid's GCD algorithm because we're going to make use of it. Now, I'd like to briefly review a few more properties of numbers. Let m be an integer that's at least 2 and not necessarily prime. Just as before, Zm is the set of all integers between 0 and m minus 1. Now, Z star m consists of all numbers a in Zm that have the property that they are relatively prime with m. That is, numbers a such that the GCD of a and m is 1. In the context of the discrete log problem, we defined Z star m for the special case where m is prime. And in that case, Z star m consists of all numbers in Zm except 0. Here's an example where m is not prime. Let m be 21. Here are the sets Z21 and Z star 21. You can see that 3, 6, and 7, and several other numbers in Z21 are excluded from Z star 21 because they have common factors with 21. It turns out that Z star m is always a group under multiplication modulo m. The key property that makes this so is that if the GCD of x and m is 1, then x has a multiplicative inverse modulo m. Now, let's take an element of z star 21 and list all of its powers. Suppose we pick 5. The powers of 5, 5 to the 0, 5 to the 1, 5 to the 2, etc., are this sequence. Notice that it's periodic. 5 to the 6 is 1, and then the subsequent powers repeat the same sequence. The periodicity is 6. If we pick 4 instead of 5, then the periodicity of the sequence is different. The powers of 4 are 1, 4, 16, 1, 4, 16, etc. So the periodicity is 3. Related to all this, we define the order of A modulo m as the minimum positive r such that A to the r equals 1 in mod m arithmetic. Equivalently, the order of A mod m is the periodicity of the sequence of powers of A. Now we can define the order finding problem as follows. The input is a modulus m, an n-bit number, and an A in z star m. The output is the order of A mod m. Note that the brute force algorithm for this is to compute the sequence of powers of A until a 1 is reached. That takes exponential time when the modulus is an n-bit number because the order might be large. It can be roughly as large as an n-bit number. Is there a polynomial time algorithm for the order finding problem? But let's pause and consider the question, why should we even care? The order finding problem might come across as an esoteric problem that we should only care about if we have a particular interest in questions about computational number theory. But one reason for us to care is that the factoring problem reduces to the order finding problem. So if we can solve the order finding problem efficiently, then we can use that to factor numbers efficiently. There is no known efficient classical algorithm for the order finding problem. This problem is essentially equivalent to factoring. What I'm going to do next is show how any algorithm, classical or quantum, for the order finding problem can be turned into an algorithm for factoring. For simplicity, I'm going to explain it for the case where m, the number to be factored, is the product of distinct primes, p and q. That's the hardest case, and the case that occurs in cryptographic applications. So our input is m, an n-bit number, and our goal is to determine p and q. The first step is to select an a from z star m and use our order finding algorithm as a subroutine to compute the order of A mod m. Let R denote the order of A mod m. Note that since A to the R equals 1 in mod m arithmetic, the difference between A to the R and 1 is a multiple of m. In other words, m divides A to the R minus 1. Now, the order of R is either an even number or an odd number. It can go either way depending on which A we pick. Define an A to be lucky if the order R of A mod m is an even number. Something interesting happens when R is even. In that case, A to the R is a square with square root A to the R over 2. And we can express A to the R minus 1 using the standard formula for a difference of squares. A to the R minus 1 equals the product of A to the R over 2 plus 1 and A to the R over 2 minus 1. M divides this product, so PQ divides this product. since p and q are primes, each one of them either divides the first expression or the second expression. It's a well-known fact that if a prime divides a product of two numbers, then it must divide one of them. So there are three possible cases. Either p divides the first expression and q divides the second expression, or p divides the second expression and q divides the first expression, or p and q both divide the first expression. Wait, have I missed a fourth case? What about the case where p and q both divide the second expression? That case cannot occur. Can you see why? In that fourth case, we would have m dividing a to the r over 2 minus 1. So a to the r over 2 minus 1 would be equal to 1 mod m. This would contradict the definition of r being the order of a. R is the smallest power of a, that's 1. So a to the r over 2 cannot be 1. So there is no fourth case. Now, among the three cases that can occur, the first two, where there's a split, are the good cases. So let's revise our definition of a lucky A. We call A lucky if two conditions hold. First, the order of R is even, and second, one of P and Q divides a to the r over 2 plus 1, and the other one divides a to the r over 2 minus 1. So there's a split. When this happens, we can easily factor m, because in that case, the divisors of m are p and q, but only one of these divides a to the r over 2 plus 1. Therefore, the GCD of a to the r over 2 plus 1 and m is either p or q, and we can evaluate this expression efficiently. A to the r over 2 can be efficiently computed by the repeated squaring trick, and the GCD can be computed using Euclid's algorithm. This is all fine if we have a lucky A to start with. So, how do we find a lucky A? I have bad news and I have good news. The bad news is that there is no systematic way known of finding a lucky A efficiently. That sounds quite discouraging. But the good news is that it can be proven that for any m, at least half of the elements of z star m are lucky. So what we can do is pick A randomly from the set z star m. The resulting procedure successfully factors m with probability at least 1/2. If it does not succeed, we merely have to pick another A randomly. By repeating the process, we can boost the success probability to be very close to 1. So that's how an efficient algorithm for the order finding problem can be used to factor a number efficiently. Okay. Now we can focus our attention on finding an efficient algorithm for order finding. The input to the order finding problem is m, an n-bit number, and a, an element of z star m. The output is the order of a mod m. Our approach will be to use the framework of the phase estimation algorithm. Recall that for this framework, we need a unitary operation and an eigenvector. Consider the unitary operation U that for all b in z star m maps ket b to ket ab, where by ab we mean multiplication of a and b modulo m. Consider the state psi1 defined as a uniform superposition of the powers of a from a to the power 0 up to a to the power r minus 1, with respective phases being the negative powers of omega, where omega is a primitive rth root of unity. What's interesting about u and psi is that psi is an eigenvector of u with eigenvalue e to the 2 pi I times 1 over r. So If we can determine the eigenvalue, then we can determine 1 over r, and if our approximation of that is good enough, we can use it to deduce r, the order of A. To see why this is so, look at what happens if we apply u to psi. This maps ket a to the k to ket a to the k plus 1, where there's a wraparound at the end with ket a to the r minus 1 wrapping around to ket 1. So applying u rearranges the kets so that the phase associated with ket a to the k changes from omega to the minus k to omega to the minus k minus 1. And this is equivalent to multiplying the state psi 1 by omega. The phase estimation algorithm uses a multiplicity-controlled U gate and an eigenvector of U. In order to get an efficient algorithm, we need to have a way of efficiently computing a multiplicity-controlled U gate, and we also need a way of constructing the state psi 1. Let's start with the multiplicity-controlled U gate. We subscript U by m and a to highlight the fact that the definition of U depends on what a and m are. For each b in z star m, the effect of applying U to ket b is to multiply b by a in the ket. There's a technical detail about what U does if b is the binary representation of an integer that's not in z star m. In that case, U can be defined to just do nothing, as indicated in the footnote below. The interesting case is where b is in z star m. Here's a multiplicity-controlled U gate with 2n control qubits. For a 2n-bit integer x, the gate maps ket x ket b to ket x u to the x ket b. That is, U gets applied x times. Of course, that's equal to the ket of a to the x times b. Can we compute this efficiently? Yes, we can of course use the repeated squaring trick for the exponentiation. The number of gates is order n squared log n. You might wonder why we set the number of control qubits to 2n. Why 2n bits? It's because the result of the phase estimation procedure is not r but an approximation of 1 over r, and we need this approximation to be 2n bits in order to be able to deduce r from it. Note that r ranges between 1 and m. Those are all the possible values of r. Here are the positions of the reciprocals of these values on the real axis. The phase estimation procedure, when it succeeds, gives a binary fraction that approximates 1 over r. The error bars around that binary fraction should be sufficiently small to contain a unique reciprocal. The gap is smallest between 1 over m and 1 over m minus 1. For those numbers, the gap is around 1 over m squared. If m is an n-bit number, the square of m is a 2n-bit number. It follows that 2n bits precision is necessary and sufficient to uniquely determine r. Okay, so we have a good multiplicity-controlled U gate that we can implement efficiently. Next, there's the matter of constructing the eigenvector psi 1. Of course, if we already know what r is, this is straightforward. But we don't know r at this stage. R is what we're trying to determine. It seems very hard to construct this state without knowing what r is. This is a serious problem. It's not known how to construct this state directly. What we're going to do is perform order finding in a different way, but uses something else than the state psi1 in the target register. Let's consider alternatives to the eigenvector psi1. Here are some other eigenvectors of U. Psi2 is like psi1, but with negative powers of omega squared. Psi3 powers of omega cubed. Psi-k powers of omega to the k, all the way up to psi-r, which is based on powers of omega to the r. The corresponding eigenvalues have parameters 1 over r, 2 over r, k over r, up to r over r, which simplifies to 1. Now, suppose that we had a method that produced a random sample from this list. Suppose that the output of the procedure was a pair k psi k, with each possibility occurring with probability 1 over r. Could we then construct r from this? Please pause to think about this. Yes, we can get an approximation of k over r from the phase estimation algorithm, and then divide the approximation by k to turn it into an approximation of 1 over r, and then proceed from there as before. Now, let's change things slightly. Suppose we have a way of generating a random psi k, but without the k. So we're supposing that we have a procedure whose output is a random psi k, uniformly distributed among the r possibilities, but where the procedure does not produce the value of k itself. Can we still extract r from this? This makes the situation trickier, but it's still possible. We can essentially extract both k and r from this. Let's consider this problem. R is between 1 and m, and k is between 1 and r. After applying the phase estimation algorithm to psi k, we are given an approximation of the rational number k over r, and we want to figure out what k and r are. To be clear, we have no information about k and r, except what we can deduce from the approximation of k over r. To get a sense of this problem, let's look at the case where m is 8. What are all the possible rational numbers in that case? Here are the rational numbers with 8 in the denominator: 0, 1/8, 2/8, which is 1/4, 3/8, etc. Now, here are all the rational numbers with 7 in the denominator. Here are the rational numbers with 6 in the denominator. And here are all the rational numbers with 5 in the denominator. We can stop there because denominator 4 or 2 is covered by the case of 8 in the denominator: 1/4, 1/2, and 3/4. And denominator 3 is covered by 6 in the denominator. So these numbers are actually all of the possibilities. Let's put them together. Our number is one of these. Notice the variations in gap sizes. What we're given is an approximation of one of these numbers. Again, we need for the approximation to be good enough so that the error bars around our approximation cover just one point from this set. And again, it turns out that the smallest gap is at the ends and is around 1 over m squared. Therefore, 2n bits is the correct level of precision to narrow down to a unique rational number, k over r, that's close to the approximation. But how do we find the rational number? If m is an n-bit number, then there are exponentially many possible rational numbers of the form k over r to search among. So a brute force search is not going to be efficient. It turns out that there is a known algorithm that solves this problem. It's called the continued fractions algorithm, and it's much more recent than Euclid's algorithm. It's only around 400 years old. It was discovered in the 1600s by Christian Huygens, a Dutch physicist, astronomer, and mathematician who made several amazing contributions to diverse fields. He's considered to be perhaps the world's first theoretical physicist. The algorithm for our present problem is called the continued fractions algorithm because it relates to the theory of expressions like this, with many levels of nested inversions, which are called continued fractions. But there is one problem with what the continued fractions algorithm produces, that of reduced fractions. The problem of reduced fractions is that different k and r can correspond to exactly the same number. For example, if k is 34 and r is 51, then the rational number 34 over 51 is the same as the rational number 2 over 3. You can divide both the numerator and denominator by 17. The continued fractions algorithm only provides a k and r in reduced form, which does not necessarily correspond to the actual r. If it happens that the greatest common divisor of the actual k and r is 1, then this problem does not occur. In that case, the fraction is already in reduced form. Recall that in our setting, we are assuming that k is uniformly sampled from the set containing 1 to up to r. What can we say about the probability of such a random k being relatively prime to r? This quantity is the ratio of the size of the set z star r to the set zr. The ratio need not be constant, but it is not too small. It is known to be at least 1 over log r in size. When the modulus is n bits, this lower bound is at least 1 over log n. That means that log n repetitions of the process is sufficient for the k that's relatively prime to r to occur with constant probability. Procedurally, in the case where the GCD of k and r is greater than 1, the result is an r that's smaller than the order, which can be checked by computing a to the r and noticing that it's not 1. That repetition just introduces an extra log factor into our running times, so it's not a big deal. But in fact, we can do better than that. If we make 2 repetitions, then there are 2 rational numbers, k1 over r and k2 over r. Call the reduced fractions that we get from the continued fractions algorithm k1 prime over r1 prime and k2 prime over r2 prime. The actual r is a multiple of r1 prime and r2 prime, and it turns out that the probability that the least common multiple of r1 prime and r2 prime is the actual r is a constant, independent of n. So, with constant probability, we can obtain the actual r from 2 runs of the phase estimation algorithm with a random eigenvector used for each run. Let's step back and see where we are. We're trying to solve the order finding problem using the phase estimation algorithm. We have a multiplicity-controlled U gate that's straightforward to compute. If we could construct the eigenvector state psi1, then we could determine the order R from that. Unfortunately, we don't know how to generate such a state efficiently. We also saw that if we could generate a randomly sampled pair k psi k, then we could also determine R from that. Unfortunately, we don't know how to generate such a random pair efficiently. Next, we saw that if we could generate a randomly sampled psi k, but without the k, then we could still determine R from that. In that case, we had to do more work, but using the continued fractions algorithm and some probabilistic analysis, we could make this work. So, can we generate a random psi k? Unfortunately, we don't know how to efficiently generate such a random psi k either. Now, at this point, you may be losing patience with this line of analysis. I keep describing alternatives to the eigenvector state, but none of them can be efficiently generated. So what's the point? Hang on. We're actually almost at a solution. What I'm going to show next is that if, instead of being given a uniformly distributed random psi k, with probability 1 over r for each k, we have a uniform superposition of the psi k's, with amplitude 1 over square root of r for each k, then we can determine R from this. And this is a state that we can generate efficiently. How do we use the superposition? Remember at the end of lecture 10 on phase estimation, I discussed what happens if the target is in a superposition of eigenvectors? In that case, the outcome is an approximation of the phase of a random eigenvector of the superposition, with probability the amplitude squared. In other words, it's identical to the outcome of a randomly generated eigenvector state, which is the case that we previously analyzed with the continued fractions, etc. So, using the superposition state is okay in the context of this phase estimation algorithm. And I claimed that the superposition state can be generated efficiently. First, let me show you what a circuit looks like that generates the state. Are you ready? It's this circuit. What? If that's the circuit, then the superposition state is just a computational basis state of ket zeros followed by a ket 1 in the last position. How can that be? Here's the superposition state, and here's an expansion of the state in the computational basis. Each row corresponds to one of the psi k's. The first row contains the state psi1. The second row contains the state psi2. And the last row contains the state psi-r. So ket A is one of the computational basis states that occurs. What's the amplitude of ket A? It's a sum of powers of omega that add up to 0. What's the amplitude of ket A squared? It's a sum of powers of omega squared that also add up to 0. And we can continue in this manner until we get to the ket A to the power r minus 1, and the amplitude is again 0. So what's left is the computational basis state ket 1, for which the amplitudes add up to 1. So we're left with ket 1. Using a binary representation in terms of qubits, this is the ket of a string of zeros followed by a 1. So the superposition of eigenvectors is indeed very easy to construct. The order-finding algorithm looks like this. The quantum circuit is the phase estimation algorithm with the target register set to a string of ket zeros followed by a ket 1. This gives us as output an estimation of k over r, where r is the order and k is randomly sampled between 1 and r. To this, we apply the continued fractions algorithm, a classical algorithm, to get a k prime and r prime, which is the numerator and denominator of the fraction k over r in reduced form. With constant probability, the phase estimation algorithm succeeds, and a non-reduced k and r are obtained, using the method of 2 runs that I described. The total gate cost is order n squared log n, and the algorithm succeeds with constant probability. Finally, let's get back to the factoring algorithm based on the order finding algorithm. The input to the factoring algorithm is m, an n-bit integer, and the output should be a non-trivial divisor of m. The algorithm that I'll describe works when m is not a prime power. There is a simple classical algorithm for the case of prime powers that I'll leave as an exercise. The algorithm chooses a random non-zero element a from Zm. It first computes the GCD of a and m to check if a is in Z star m. If so, then it computes r, the order of a mod m. This is the quantum part of the algorithm. Then it computes the GCD of a to the r over 2 plus 1 and m. This part makes sense if r is even and can be computed by the repeated squaring trick and Euclid's algorithm. With probability at least a half, this succeeds in finding a factor of m. What happens if the GCD of a and m is greater than 1, so a is not in Z star m? Well, we could select another a, but we don't need to do that, because if the GCD g is greater than 1, then g is a non-trivial factor of m, so we can just output g in that case. In summary, the probability of this factoring algorithm succeeding is a constant, and it can be implemented with order n squared log n gates. Okay, let's end this lecture now.